Okay, welcome back everybody for the last talk of the symposium. It's been really nice to see, such a diverse set of topics, I think. And we're going to hear lastly from Tim Hsieh from Perimeter Institute. Tim has done, a really wide body of work covering topics from dynamics to novel algorithms, all kinds of applications to condensed matter systems, and then especially topological phases of matter. So he's going to tell us about how to realize these in quantum computing. Great.
Okay, great. Yeah, thanks a lot. Thanks a lot to Miles and John for organizing this. It's been a very enjoyable day. And yeah, thanks to all of you guys for staying till the very end. I'll try to be as minimally technical as possible. And also don't hesitate to ask any questions in the middle. All right, so this talk is basically about how to access quantum many-body states, in particular long-range entangled states, on both quantum computers and on classical computers. So I don't need to remind you of the amazing progress that has been made on quantum computing hardware. There are a variety of platforms such as trapped ions, superconducting circuits. And so this really motivates us condensed matter physicists to think about ways to use these new devices to realize phases of matter that we're interested in that are hard to realize by other means. Say, to define them in a real material might be hard. So can we realize them synthetically in these up and coming systems? And in particular, what we were interested in is how to use not only unitary evolution, but this non-unitary thing called measurements, which is also fortunately available to us, to speed up the realization of these long-range entangled states. So that'll be the first part of the talk. The second part of the talk is not meant to be carried out on quantum computers. It's more meant as a new classical approach to many-body physics. But again, we're interested in how can we use this non-unitary thing called imaginary time evolution to write down these efficient variational wave functions that we can optimize on our classical computers. Okay, so the first part, using measurements meant for quantum hardware, was done in collaboration with Peter, who's a postdoc at Perimeter. Leo is a PhD student, and Isaac from UC Davis. And the second part, this classical approach using imaginary time evolution, was done with Matt, who's a PhD, this is several years ago. He's graduated, moved on to quantum computing industry. Roger, I think most of you know from Perimeter, UW, and Tarun from San Diego. And also mention some more recent work along this imaginary time direction, done with Roche from Cornell and Guifrey from Google. Okay, so let me first briefly introduce what I mean by long-range entangled quantum matter. So very roughly, it's quantum matter that's very far from classical product-like states. Okay, so a typical example of this is topological order. Okay, so unlike conventional order, like this ferromagnet here, topological order cannot be characterized by any local order parameter. Okay, instead, it's characterized by much more interesting properties. For example, there are fractionalized quasi-particle excitations in topological order called anyons that can be neither bosons nor fermions. And so due to these, very interesting physical properties, these topologically ordered states have been very sought after in experiments. And indeed, you might have heard of some of these recent experiments from Rydberg group at Harvard, MIT, or from the Google group with superconducting qubits, in which they, try to realize these topologically ordered states on their hardware. Okay, but what makes these states very interesting also, almost by definition, makes them hard to realize. Okay, so more specifically, I said they're far from classical product-like states, and what I mean by that is that they cannot be prepared from trivial product states using unitary local quantum circuits with constant depth. So with depth not scaling with the system size. And why is that? That's basically because these local unitary circuits are constrained by a light cone, right? There's this emergent light cone in a local unitary circuit, which bounds the speed at which correlations can be established for faraway points. Okay, and that means that to produce the requisite long-range correlation in these long-range entangled states, one needs circuit depth or circuit time scaling with system size in order to prepare these states. So this is the state of affairs for local unitary circuits. Okay, so but what about measurements? Right, measurements are non-unitary, so they can presumably violate this Lieb-Robinson bounds which constrain unitary circuits. So can we use them to speed up the preparation of long-range entangled matter? Yeah.
So, in trying to quantify just how difficult it is to realize these things,
Yeah.
the resources, it seems like based on what you're saying is that the resources needed is, I'm going to be interested in large collections of qubits and L, and with a number of gates also scaling with depth scaling as on order L.
Yes, that's right.
Why is that very difficult?
Well, I mean, ideally we want as big of a system as possible, right? Like eventually we want to do like any-on braiding, to see these fractional statistics. We need a very big system. So that means that we need also a very big time direction, right? Of order L, right? But which is still, I know.
Yeah,
so
I guess just as a contrast, if you were thinking about the quantum algorithms that are exponentially difficult with translate them into exponentially long runtime.
Yeah. Those would be even in a different category. So indeed, depth of order L will not completely kill you. And indeed, these Rydberg particularly qubit experiments, they are using local unitary, and they do claim to prepare states in these phases of matter, right? So in the intermediate, number of qubits regime, it's reasonable, but as we scale to more and more qubits, eventually we need to worry about coherence times, things like that, right? So ideally we want constant depth circuits, right? Okay, and this is not simply an academic question. As we heard from Michael, for example, many of these quantum hardware approaches already have or are trying to develop this capacity to do mid-circuit measurements. This is because everyone eventually wants to do active error correction toward fault tolerance. And so it's natural to try to achieve this capability. Okay, so this is the type of circuit we want to consider. So let's just call this a local adaptive circuit. So let me just highlight several of the important features. So we allow for local unitaries, we allow for local measurements, and we also allow for the classical outcome of the measurements to be broadcasted non-locally through the system and used to inform the choice of future operations. That's what the adaptive means. We make use of all the classical outcomes to determine what to do at future times. And we'll also allow for a finite overhead of ancilla spins. It's basically like order one number of copies of the system to use in the scheme. Okay, so the question is, what can we do with this type of circuit now? So in our work, we focused on three pretty general approaches to try to use local adaptive circuits to prepare long-range entangled matter. So the first one I'll talk about is inspired by tensor networks. And I think one advantage of this approach is that it's modular, it's parallelizable, and it's pretty friendly for near-term experiments. The second one is inspired by renormalization. And the nice thing is that we're able to efficiently prepare quantum critical states using this approach. And finally, the last one is based on what's called a parton construction, which I'll tell you about more later. And the cool thing is that from that, we get efficient ways to prepare chiral topological order. These are things like the spin analogs of fractional quantum Hall effect, for example. Yeah.
So when you were just talking about the features, after you measure a qubit, is one of the features that you can reuse that?
Yeah. So you can do whatever you want after the measurement. Yeah.
You get to use that qubit again.
Yes. Right. Okay. So yeah. So these are the three general approaches which I'll present. And we're not the first to consider this question of how to use measurements to facilitate long-range entanglement preparation. There are these older, so this actually dates far back to Briegel and Rossendorf, in which they find ways to prepare things like GHZ state, toric code quickly. There's been a pretty recent revival of interest in the subject, but what we contribute are these three new and fairly general approaches. Okay, so let me just remind you of the toric code state. I think many of you already know this, but just in case, let me give you the essential facts. So this is a canonical example of topological order in 2 dimensions. And so it's defined on the qubits, which live on the links of a square lattice. And it's convenient to define spin up to correspond to having no string on this link, and spin down to correspond to having a string on the link. Then the toric code state is simply the superposition of all closed loop configurations of these spins. Okay, so this is like a nice picture of topological order. And tensor networks conveniently capture this picture very naturally. Okay, so I'm preaching to the choir here. I'm glad I don't need to spend much time introducing tensor networks. So in brief, the tensor network for toric code involves this G tensor, which just broadcasts the state of the physical spin to the virtual legs, and this T tensor at each vertex, which guarantees this closed loop condition I mentioned. So it basically ensures that every string that comes in must come out. So there are an even number of strings around every vertex. Okay, so this is how the toric code constraint is naturally built into this tensor network. Okay, so how do we get adaptive protocol from this tensor network? Well, it's quite simple. So let's first imagine this vertex tensor to actually be a physical state we prepare, say, in the lab. Okay, so this 4-qubit tensor is just some wave function that I've defined. And so we can prepare many of these 4-qubit vertex tensors in parallel. These are just easy 4-qubit states. And then we measure ZZ for every pair of qubits on a link. And so now this basically stitches the tensor network together. Okay, so we measure ZZ on every link. And after that ZZ measurement, those 2 qubits now have 1 effective qubit degree of freedom left. And if all the ZZ measurements, if all the ZZ outcomes were 1, then it's pretty easy to check that you get the toric code on this effective system. Okay. So I've assumed that the ZZ measurement outcome is uniformly 1, but of course you want to deal with all possible outcomes. And this is very simple. It turns out that the wrong outcomes, if you get ZZ minus 1, those actually correspond to anyon excitations in the toric code model. And those can be corrected easily by applying a string operator, so a product of x's, which connects the defects or the locations of the wrong outcome. Okay, so basically we do these ZZ measurements. Sometimes we get -1. They come in pairs, and they can be paired up with simple string operators of Pauli's. Okay. So yeah, so basically the correction, the measurement, the vertex preparation, they're all constant depth here. And this protocol generalizes to many topological orders, which have tensor network representation, such as the double semyon order. And again, it's a modular approach that may be suitable for particular quantum hardware platforms. Are there any questions on this tensor network based idea? Yeah. Yeah, yeah. Just a projection operator 1 plus z1 z2 over 2. Yeah.
Oh, but you specifically can't measure each qubit individually, right? Is that right?
We're not measuring them individually.
Just
look,
want to learn their parity.
yeah. Right. Yeah. Mhm.
Is there a similar, so this so I guess there are like, you know, the degenerate ground states for the toric code.
Yes,
Or
right.
ground state. Are there simple tensor network instructions for like any state in the ground state manifold?
That's a good question. Right. So yeah, indeed, here we construct a particular sector because that's dictated by the initial state, which is the all plus state. So okay, each of the 4 sectors has an efficient tensor network because you can just locally flip a spin in the initial state to change sectors, right? But for a general superposition, I would think so, but I'm not sure what the explicit construction is. It's definitely still low entangled, so probably. But yeah, let me think about the details later. Yeah. Any other questions? Okay, so the second approach is based on this idea of renormalization, which is also another old idea in physics. And basically, renormalization is just a reorganization of your degrees of freedom into those that matter most at different length scales, right? So, for example, in this. Okay, again, you're all familiar with Mera already, probably. So in Mera, we begin with a full many-body wave function, and we apply some disentangling unitaries and disentangle some degrees of freedom. So those are the degrees of freedom that matter for short distance properties, but not for long distance properties. And so we can iterate this disentangling procedure and get fewer and fewer degrees of freedom until finally we have a very sparse system. And those are the degrees of freedom in which that matter most for IR observables. But as I think Michael pointed out in the morning, this Mera can be equally well viewed as a unitary circuit applying in reverse, right? So we can start out with all these product of zero states and just apply these unitaries to construct this many-body wave function. Right, so this Mera for a system of size L has a depth log L due to this hierarchical or tree-like structure. Right, so one gets a unitary circuit for preparing a state at finer and finer length scales, but the catch is that this unitary circuit is non-local, right? As you can see, as you go higher up in the circuit, these unitaries you need to apply a couple degrees of freedom that are farther and farther apart. Okay, so how can we get a local but adaptive circuit from this? Well, again, it's pretty simple. So each non-local unitary gate can be realized as a finite depth adaptive circuit using pretty much a teleportation trick. And I'll just spell this out briefly in the next slide. And what this means is that each of these operations is now a local adaptive block. And so the whole circuit becomes a local adaptive circuit of log depth. So, right, so how does this non-local unitary to local adaptive mapping work? Pretty much through the teleportation trick, or sometimes what's called entanglement swapping. So say you have like these 2 red qubits which you want to apply a unitary gate on, but they're very far apart. Well, what you can first do is you can create these bell pairs in between just by doing bell pair measurements. And to get this red qubit near the other one, you can just apply these bell pair measurements on the offset dimers. So after that, those bell pairs, those dimers collapse into bell pairs, and this red qubit gets teleported all the way here. And then you can apply your local unitary gate there and then teleport back. Okay, so that's how a 2-qubit non-local unitary gate is a simple local adaptive circuit. Okay. And notice that for this case, it's important that we have ancilla degrees of freedom, right? Because the physical spin in the physical spin chain, all these degrees of freedom in between are participating in some many-body wave function already, right? So to apply this extra unitary gate, we need this extra ancilla backbone to do the teleportation and teleport back. Okay, so as I'm sure you all know, Mera is quite powerful in 1D. It approximates quantum critical states very well. And in fact, it exactly captures many topological orders of interest, pretty much all string net models, all quantum double models. So it's quite a nice description. And so using Mera plus this reduction to local adaptive circuits, we find that you only need log L depth local adaptive circuits for preparing all of these states. And this is pretty much optimal for at least 1D quantum critical states, because you might know that 1D quantum critical states have a logarithmic, sorry, if you bipartition a quantum critical state in 1D, the amount of entanglement scales as the log, the size of the partition, right? So this means that you need a circuit depth of at least log scaling to capture that state accurately, even with measurements. Okay, any questions on this Mera thing? Yeah.
Maybe a little bit out there, but I think in the tutorial, someone asked, how do you do long-range gates classically? And the trick I know is you can sort of stretch a 2-qubit gate into the Numerically, I think the rank is like 4 in the general case. And I was wondering if you see a connection with teleportation. Do you use the same trick in size? Like 2 bell pairs would be 4 rank, and it sort of accomplishes the same thing by stretching of the 2-qubit gate. I don't know if you know. What?
Sorry, so how to do a long range 2 qubit gate class? Like, what do you mean classically here?
You can do it as a matrix that you have, because it's like you cut it between the 2 qubits, and then you sort of stretch it out. You can make it easier to network that acts far away, like across, a large system. In a way, it's like all the tensors in the field of Go are just kind of carrying the information about the action through space with the other one. It seems to accomplish something quite similar. So
to teleportation.
And you're calling it classical just because it's the MPO?
Yeah. It's like just that we use it as a classical trick.
I see. Yeah.
Like thought of it that way.
Yeah, no, it's a good point. Thanks. Okay, so the third approach we came up with is to use what's called a parton construction. So partons are also an old idea from physics, in particular particle physics. So we all know that protons and neutrons are made out of quarks, which are typically confined, but at very high energy, high temperature, or high pressure, they can become deconfined. But in topologically ordered matter, it's quite interesting that these deconfined partons can actually emerge. So they're not fundamental degrees of freedom. So in other words, we have like these materials, phases of matter, which we start out with, say, spins, or we start with electrons. But due to the nature of their interactions, the excitations that emerge are actually unlike the original degrees of freedom. Right? These are the anyons I mentioned. And so this parton construction or parton description really captures this idea of fractionalization explicitly. So here's a explicit construction of this parton type. One can imagine decomposing a spin 1/2 degree of freedom into 4 Majorana or real fermions, shown here. And then you can do whatever you want with the Majorana fermions. But at the end of the day, you have to remember that you're starting out with a spin 1/2 degree of freedom. Yeah, so what I mean by that is the Hilbert space of these 4 Majorana or real fermions is equivalent to the Hilbert space of 2 complex fermions, which has dimension 4. But your original spin 1/2 is only a 2-dimensional Hilbert space, right? So you need to impose a constraint to project the Hilbert space of these 4 Majoranas back to the original spin Hilbert space. So you do that by just demanding that the product of these 4 Majoranas is 1, or the identity. Okay. So how do we use this building block, this description of a spin 1/2 in terms of 4 Majoranas to construct interesting phases of matter? Well, let me first show you a trivial example of this. So let's say we have a bunch of spins and we pair the Majoranas within each spin. By that, I mean that we're considering a state in which the product of the 2 Majoranas is identity, or 1. Okay. Then this is a manifestly trivial phase where each spin is just doing its own thing, right? So it's a product state of spins, and in this case, the partons, these Majorana partons, are confined. They can't move around freely. Okay. However, here's a much more interesting state in which now we've paired Majoranas from different spins together. Okay, and this, you can convince yourself, is a deconfined model. Here the Majoranas are free to move around. And why is that? So we can try to drag, say, this left Majorana all the way to the right by applying a string operator of Pauli x. Okay, and since these 2 Majoranas and these 2 Majoranas were already in a definite state in which they take value 1, pretty much the middle of the string doesn't cost any energy. Okay, so this means that this Majorana can be dragged arbitrarily far away, and the only energy cost comes from creating the Majorana excitation, the endpoint itself. The bulk of the string costs no energy. So this is the definition of deconfinement. So one can check that this parton construction gives you a spin wave function that's actually equivalent to the Tor code topological order I described earlier. Okay, so how do we get an adaptive circuit from this parton description of topological order? So again, it's quite simple. First, we prepare the simple parton state. So imagine we have all these Majoranas, and we prepare this essentially a product state of these Majorana dimers. This can be done because, again, the whole system is just decoupled pieces. And then we measure the 4 Majorana operator that should correspond to each spin. And again, due to the randomness of measurement, sometimes we get +1, sometimes we get -1. And we want the state in which it's +1 that corresponds to applying this projection operator going back to the spin Hilbert space. But we get -1 sometimes. But similar to the Tor code correction earlier, one can apply a product of Majorana operators connecting defects, or connecting where the outcomes are -1, to annihilate the defects and get the target state. Okay, so right, so again, each of these operations is some simple order 1 depth protocol. So this parton motivated adaptive circuit can be generalized to many different parton models, which give you a vast array of topological phases of matter. So there's one famous example of this in the Kitaev honeycomb model. So here you have spins on the sides of a honeycomb lattice. And as I showed you earlier, the trick is to fractionalize each spin into 4 Majoranas and enforcing this constraint on the 4 Majoranas. And then depending on which state you put these 4 Majoranas, you can construct many different types of topological order. So in particular, if you put these C Majoranas into what's called a chiral superconductor state, then when you project back into the spin Hilbert space, you get a chiral topological order. In fact, a chiral non-abelian topological order. So this is an example where we get via this parton construction an adaptive circuit which prepares chiral topological order, which at least before this approach, I wasn't aware of any other way to get chiral order. Okay, Yeah, that's what I wanted to say for now on this use of measurements to speed up the preparation of long-range entangled phases. Let me pause for any questions here. Yeah.
When you do the interpretation, you use the ansatz. Are they like, do they entangle with the system, or can you reinitialize the after you teleport back?
Yeah,
Or-
exactly. That's why you need the ancilla chain to begin with. So you first prepare the Bell states on the ancillas, use them to teleport, and then you need to reinitialize them in some other Bell state to teleport back, right?
And you don't affect the system.
You don't affect the system. Yeah, the system is just being that many body wave function that's being constructed, right? Yeah.
And if I'm just thinking about implementation, like the ion trap that Michael talked about this morning.
Right.
Where you really can just move your qubits around.
Mm-hmm.
You don't, am I correct in that you don't need the ancilla for any other part of that local adaptive circuit?
Which one in the Mera construction? You might need that ancilla to do teleportation for another layer of the Mera circuit, right? So let me just right. So one might need to do teleportation for many of these non-local gates, right? So each implementation of a non-local gate might use that ancilla like right behind it.
Yeah.
Right.
But in the implementation where you can just move your qubits around.
Yeah.
And apply local gates.
Oh, okay. Right. So they're
Right.
right. So yeah, it's a good question to compare, say, this adaptive scheme with measurements to the power of non-local unitary gates, right? So indeed, there are some trade-offs. Like as Michael said, moving it physically may incur some errors, but yeah, I think it'd be interesting to just compare the two approaches on the actual hardware. Yeah.
Is it true? I think so. For the toric code example,
Mhm.
there's a more like stark dichotomy, right? Like even with long range gates, you still need at least log system size depth. Is that true? I think.
Yes, yeah. Right. So for toric code, with non-local unitary gates only, you would still need a log depth circuit.
And the same for the mirror.
That's right. The mirror is logged out, right?
Although here it seems like it's log depth no matter how you cut it, right? Like
Yeah,
it's
yeah.
log depth with either long range gates or with measurement forward and local gates, right?
Right.
Okay.
Yeah. Okay. So sorry. I think I went to another talk by accident. Yeah. Okay. Right. So let me switch gears pretty much completely and now talk about a classical algorithm. So forget about any implementation on quantum hardware. It would be amazing if this were possible, but I doubt it. So this is a classical approach that also makes use of non-unitarity, imaginary time evolution. So the ansatz is quite simple. So let's say we're given a many-body Hamiltonian H. That's a sum of two pieces, HA and HB, which are each simple in some way. Okay, so think Hubbard model where you have like, kinetic term of fermion hopping and Hubbard interaction. That's just on-site interaction. Many Hamiltonians are of this form. Okay, so the ansatz we want to consider is obtained by starting out with some simple initial state psi naught, and then alternating between imaginary time evolution with these two pieces of the Hamiltonian with some imaginary time alpha and beta that's to be optimized. Okay, and we can keep on alternating between these two HA and HB for as many steps as we like, say P times, capital P times. But obviously, we want smaller p. Okay. And since it's imaginary time, we need to normalize at the end of the day. So this is the ansatz we want to consider. Okay. And it's motivated by the real-time version of this, which many of you may know under the name of QAOA, or quantum approximate optimization algorithm. It's basically just you put an extra I here. Yeah, so we were kind of motivated by QAOA to consider the imaginary time counterpart, which again, as you'll see, can be much more efficient because of the fact that it's actually non-unitary, right? So as usual, it's good if ansatz has some guarantee of working at least in some limit, and this is no exception. So if you take this parameter p to infinity, so if we allow for infinitely many back and forths between HA and HB, then this is guaranteed to approximate the ground state of the initial Hamiltonian, and that's because one can consider just imaginary time evolution with a full Hamiltonian itself for infinite time. That'll project you to the ground state of H, and then you can always trotterize that into a circuit of this form if you're allowed, let's say, infinitely many trotter steps, of course. So it's guaranteed to work in the limit that p goes to infinity, but as I said, we're interested in the limit of small p. And we're interested in what happens when these time steps actually are finite and variable. They're to be optimized. So it turns out that for the Hubbard model, this type of ansatz has already been considered by these people. But we wanted to, consider first a solvable example where we can see exactly how well this ansatz scales. Okay, and for that purpose, it's great to revisit our old friend, the transverse field Ising model in one dimension. So just to remind you, this transverse field Ising model consists of both nearest neighbor ferromagnetic interaction and paramagnetic term. And so we're interested in targeting the ground state of this model, which for these parameters is critical. It's at the phase transition between the ferromagnet and a paramagnet. So again, just to remind you, our variational ansatz for this critical wave function, yeah.
Just a minor detail. Are you allowing the betas and alphas to be complex? Because if so, you would kind of interpolate between QAOA and.
It's a very good question. So here we're just restricting them to be real. If you allow for a mixture, like I think we played around with that a little bit and found that imaginary time, like dedicating the parameter to imaginary time is preferable. Like having the unitary part did not really help much. Yeah.
You didn't say this explicitly, but I would think that because HB and HA don't commute.
Yeah.
Somehow the notion of kind of like alpha and beta becomes smaller and smaller and smaller if you take the large P limit. So you're never going to get the right answer if you stop at finite. Is that right? And without taking beta and alpha, I would think that if you don't take beta and alpha to the infinitesimal event, you're not going to approximate the ground state. Or is that not?
Well, as you'll see, yeah. Right. So again, this is the structure of the ansatz we consider. And here, the initial state we start out with is just the paramagnetic plus state, the product state. And HA is this ferromagnetic part, and HB is this transverse field part. Okay, so first let me show you the results for the relative error in energy that we get for the optimal ansatz as a function of the number of pairs of parameters. So as you can see, it does remarkably well. Even for p equals 2, which is 4 variational parameters, you already get a very small relative error in energy of 10 to the minus 4 for a fairly large system of 1,000 sites. But some of you might be worried that relative error in energy can be misleading, right? Especially for a critical system where there are many low-lying states. So we can also look at the error in fidelity with the exact ground state. And so this is error in fidelity versus system size on log-log plot for different numbers of variational parameters. So the shaded region is what each fixed P can achieve. So as you can see here, one can roughly see that to get a target fidelity, you need the number of parameters P that scales with log of system size. Okay. And one can make a more direct comparison with the projector.
Alpha and beta are not, they're just fixed and you're applying the same sort of.
No. They vary from step to step. Yeah, it's not like a Fouquet imaginary time. It's
How do they vary?
that's a good question. So they're yeah, I mean, well, let me just the short answer is we don't have an analytic understanding of this, but there seems to be some nice pattern as a function of P. Okay. I don't know. Yeah. So these are the optimal alphas betas for algorithms using different P, targeting this critical state.
Someone asked in the chat how you choose the optimized alpha.
Through the usual tricks of like gradient descent. Yeah.
So seeing this, it looks like the story possibly be that if I'm reading this correctly, it's like the earlier alpha and beta is like first or smaller, and then the later ones are bigger. As you get
No. So sorry. Yeah. You should focus on a fixed P here, right? And then just yeah. So here. Yeah, I think. Okay, I have to double check whether alpha 1 beta 1 is the one you apply first or the one you apply down the line. Yeah.
The closer you are to the ground state,
Mm-hmm.
the safer stuff. Like, closer to the United States.
Right.
Imagine
Yeah.
if it already was in the ground state, then you could just, but it's kind of loose, but it's like you could, like using like TDP or one of these other. You kind of take bigger steps once they get closer to get. So I wonder if you had any.
Okay. Yeah. Let me first just confirm the convention, which is then. But I think it's also consistent with what Vadim was saying that.
Well, I'm not sure because your the point is that HA and HB
Yeah.
have very different ground.
Yes. Yeah.
Right? So
Mhm.
if you take a really huge step or a step that's too big,
Mhm.
you're gonna like, well, this system like off grid, way off grid.
Right. Yeah. Mhm.
I'm a little bit intrigued by-
Right. But it's.
Yeah, I mean, you're just projecting onto like totally the wrong thing.
Mhm.
So
Yeah, but at least it's clear that as you take P larger and larger, all the optimal angle values are coming down toward the Trotter limit.
Right.
Yeah. Right. Okay. Thanks.
One more question. Is there any
Yeah.
question about Lieb-Robinson found with imaginary time evolution? Like, is
Yeah.
the length over which you get correlations confined by the depth of the ansatz or no?
Yeah, it's a good question. I think there was some work by like Anatoly Demarsky et al. On some Lieb-Robinson type bound for imaginary time step. I don't know the exact result right now, but yeah, maybe that reference.
Yeah,
Awesome.
part of what made me wonder, I feel like the fact that the fidelity seems to increase linearly for like, it's going like log with the depth.
Mm-hmm.
And because like the correlations are decaying algebraically at the critical point, it almost feels like you must be capturing correlations at much longer range than the depth or something.
Yeah.
Make that happen.
Right. Mm-hmm.
I wasn't
Yeah.
sure if that was possible or not, but
Right.
okay.
Yeah.
Do you know how the alpha and beta depend on G, like on where you are?
I think we have plots like that in the appendix, I think. Yeah, but we have no way of driving this analytically so far, but it would be nice. Yeah.
Have you tried for nice? I mean, all this is really straightforward.
Mm-hmm. Yeah.
So you can, okay, we should talk there.
Right. Like it's okay. Naively, you might think it's a tractable analytic problem, but you're still optimizing. Yeah, like we thought quite a bit about it, but Yeah, we can talk later maybe. Okay, so we can make a more direct comparison with the projector method. So again, by projector method, I mean just evolving with a full Hamiltonian in imaginary time to get to the ground state. And so if you do this for the critical ground state here, then you need imaginary time scaling with system size. That's because the imaginary time you need goes as the inverse gap, which goes as 1/L for this critical point. So the object to compare with in our ansatz is basically the total imaginary time. That's the sum of all these optimized angles. So what we find is a nice scaling collapse for the error in fidelity with respect to this functional form that's tau times some power of log L. Okay, so what this suggests is that the amount of imaginary time we need scales as some power of log system size, which is clearly much better than this linear scaling. So somehow this bang approach of imaginary time dilution speeds it up considerably compared to the usual, say, Trotter scheme. Okay, yeah.
I know this is, but if you kind of move away from quantum algorithms for a second, does this work in 2D, just in a classical computer? Is this like a good ansatz for 2D?
Well, that's one of the points I wanted to raise at the end. So that's where I think we could use many of your expertise in the audience. So what I was about to say here is that there's a natural implementation of this for infinite matrix product states. But let me return to 2D and beyond closer to the end. Yeah. Sure.
I'm just trying to understand. There was one more form, right?
Sorry? Yeah, right.
So if I thought of the usual sort of critical slowing down type ideas, right? You would think that, what is the best case scenario for this? I would have thought that, well, we know what the gap does. The gap is 1/L.
Yeah.
Right. So if you manage to find the algorithm, maybe not this one, you would think that 1/tau should go down to 1/L.
Yeah. That's what you expect for the usual. Well, this is clearly some, like far from equilibrium dynamics. So, yeah, but I think that there's a
finite lifetime. That seems like
right.
Okay. Thank you.
Right. So recently we decided just to implement the scheme with just infinite matrix product states. Again, the obvious nice thing is that there you have access to an infinite system immediately. And the long story short is that we find consistent results with our finite size studies. So we looked at again, targeting ground states of this transverse Ising model, both at criticality and away from criticality. And we find very similar results as before, but now for just infinite systems. So the relative error in energy seems to decay pretty much exponentially with the number of parameters. And the infidelity also appears to decay exponentially with the total time for both states off criticality and states near criticality. Okay. Okay, so yeah, I think I've already insinuated that we have no understanding of why this works so well, but let me just point out some features of imaginary time evolution that indicate how counterintuitive and how powerful it might be. So, right, so clearly there's no Lieb-Robinson bound. And indeed, to prepare, say, a long-range GHZ state with imaginary time, you only need amount of time scaling logarithmically with system size, as opposed to linearly for a purely unitary local preparation. The other point I want to make is that a local operator can actually generate entanglement far away. Okay, so just as a point of comparison, consider two qubits in, say, this entangled state. Then if you apply a local unitary on, say, the blue or the green, then obviously you cannot increase or decrease the entanglement across the cut, right? The only way to change the entanglement with unitary is just to apply a unitary across that cut. However, for imaginary time dynamics, even if you apply a imaginary time evolution on one side, you can boost or reduce this entanglement, basically by reweighting these coefficients in this case. And here you can also get some intuition that the more initial entanglement you have in the state, the more the imaginary time evolution can change the entanglement. Okay, so basically I think this morning Chris mentioned this constant rate of entangling for local unitary circuits that's independent of system size. So for imaginary time evolution, that no longer holds. So the amount of entanglement you can boost in one layer is not just simply some order one number. It actually can depend on how entangled that state it was acting on earlier in the circuit. So there's this one pretty stark illustration of this counterintuitive physics that we found. So plotted here is the bipartite entanglement entropy of this ansatz as a function of the amount of time, as a function of the amount of imaginary time used in this circuit for different system sizes. So basically we apply like one layer of the ansatz, calculate the bipartite entanglement, and then look at the next layer, see how entangled it is, etc. And what you find is that the entanglement growth for this Vita ansatz actually appears to be exponential with the amount of imaginary time that was used. So yeah, this is just some numerical observations of the peculiarities of this imaginary time evolution. Yeah.
What's the exact value for the entanglement?
So it's very accurate, so it should be very close to the final point here, right? Yeah, so clearly we can only have exponential growth up to a certain point, right? Because yeah, I didn't show this earlier, but the entanglement for this ansatz at a given circuit depth is still bounded by a linear by a line. It's just that that line is steep, and so here we have an exponential like below it, but eventually it'll be cut off. Right? Okay, so one hope is that maybe we can at least try to mitigate the sign problem with the ansatz, and that's because the sign problem depends both on it depends both on space and the amount of imaginary time. So here if we compress the imaginary time direction substantially, maybe models with the sign problem are slightly more tractable. So the question is, can we make a more friendly sign problem? And indeed, the late unfortunately the late Sandro Sorella had this very nice study where he uses a related ansatz that he called the variational auxiliary field called a Monte Carlo technique, and he got very impressive results on this doped square lattice Hubbard model. So I encourage you to check this out. I think he also gave a talk at one of the Flatiron conferences a couple of years ago, but I couldn't find the recording online. But in any case, the reference is here. So yeah, I think it's quite exciting to try to see whether or not this type of imaginary time ansatz can be combined with either quantum Monte Carlo methods, as was done here, or with tensor network methods. I think 2D is, as always, is a frontier to apply this method. So maybe one of these approximate tensor construction schemes for what appears to be only a very low dimension PEPs that you need here would give a very powerful algorithm. So yeah, I'd be very interested in talking more about that. So yeah, it's getting pretty late, so let me just wrap up. In the first part, I talked about using measurements and feedback as a way to shortcut the preparation of long-range entangled matter using these three different approaches inspired by tensor networks, Mera, and partons. And in the second part, I talked about this imaginary time ansatz, which as at least demonstrated for this transverse Ising model is very efficient. And the question is for these harder models like Hubbard or frustrated magnetic models in 2D, how well can they perform? So yeah, it'd be very interesting to explore that with these new numerical techniques. And regarding the measurement side, one thing we're very interested in is like what exactly are the limitations of these local adaptive circuits? They violate Lieb-Robinson, but are they subject to any constraints aside from just bounded entanglement growth? And also in all the examples I presented, we're preparing a single pure state. So if you think about this from the trajectory point of view, by doing measurements, we're getting all these outcomes. And then by doing feedback, we're converging all these trajectories to a single target pure state wave function. But in general, we don't need to do that. So is it possible to control the trajectories in a way to prepare interesting mixed states at the end? Measurements, I view as like a very powerful tool that's hard to control, right? It's non-unitary, so you can go beyond Lieb-Robinson bounds, for example, but you have to deal with the intrinsic randomness involved. So how to steer these trajectories effectively is I think very interesting direction of research. So yeah, thanks for listening. I'll take questions.
In a big picture setting, do you think that taking a Hamiltonian that has this like easy part and a hard part and like characterizing the imaginary time evolution, do we have reason to believe that that's a good ansatz for more models than just transverse field Ising?
Yeah. So this Cirella work I showed is one example for doped Hubbard. We also looked at 2D transversalizing using quantum Monte Carlo to sample the energy for our ansatz, and we also got pretty efficient results. Yeah, I didn't really get a chance to talk about this, but this is what you get for 2D Ising for different transverse field and for 2 parameters and 4 parameters. Yeah. Yeah, so there is some evidence that it works quite well. Yeah.
I'm still kind of intrigued by your Ising change. Did you try going off criticality and seeing what happens? Is criticality a red herring here? Well, does that Lagrange become a constant?
Right. Yeah. I think it does, but I need to double check, right? So even off criticality, the usual projector would be constant scaling, right?
No, I just want to know, like,
that
optimization.
Right. Yeah. It's a good point. I think we might have some results on that. Well, actually, this for 2+1 already. Okay, we don't know about scaling here, but this shows you that criticality is like the hardest point, right? Yeah. Yeah. Right.
Somehow I'm thinking about Monte Carlo, classical Monte Carlo. That's slowing down.
Yeah.
Sometimes it's slowing down, but it's critical, and sometimes it's just forcing to try and get the domain moved out. I'm just not sure, like with this optimization, what's going on? There's a physics of it.
Right. Yeah. Ian?
Does this fail anywhere? Like if context where it doesn't work at all, that interesting anyway?
Well, so I think it's clear that it's like the representability is there for very low depth or few parameters, but the difficulty is in the optimization, right? So there, for the transversalizing models, it worked well, but maybe for problems with sign problem models, that might show up in the optimization of even these very few parameters, right? So there's no free lunch except for today, but yeah, I mean I don't think we can, solve the sign problem, but there might be some, intermediate like polynomial advantage, right? Yeah.
Sorry, do you think just to kind of back up to the end of that answer, do you think the sign problem is likely to show up in the way you're doing variational Monte Carlo to optimize this, in the sampling itself, or the difficulty in optimization in some cost landscape that makes sense?
Yeah, I don't know. It's a good question.
Usually it's associated with Monte Carlo and the difficulty of sampling, which you have, but usually people talk about variational Monte Carlo as not really being so sign problem-y as. So yeah.
I mean, so
about your.
yeah. So here as was done in the Sorella work, he used auxiliary field Monte Carlo to sample this problem with some sign structure, right? And I remember seeing a slide in his talk a couple of years ago. Okay, I think it was titled "Sign Problem Solved?" ? And there was a plot of like the average sign as a function of I think system size for fixed p, and it showed like some flattening behavior. So it seemed quite promising, and I think it needs to be explored more. But yeah. Yeah.
I was wondering the first part. Thanks for wondering if you had a good sense of like how broad of a family of like tests you realize by the kinds of protocols.
Yeah, it's a great question. So it relies on the correctability of errors here, right? So like an arbitrary tensor network does not fit into this scheme. Like, yeah, I think initially I thought that injectivity is all you need for the local tensors, but I think one needs more stringent criteria. Like, yeah, you need to be able to apply something at the physical level to correct at the virtual level, pretty much.
So like somehow the test has to realize some kind of error correcting for.
Yeah, right, yeah.